Okay, great. So let me first thank the organizers for this opportunity. I'm very happy to be here, and also thanks a lot for scheduling on the first day, so I can actually enjoy the rest of the conference. My name is Jed. I'm a postdoc at the TYQI Center for Excellence in Copenhagen. And today I'll tell you something about new analytic self-testing results for the CHSH and the tripartite membrane inequalities. And it's on the archive already, so if you want to have a look, please feel free. Okay, so the outline of the talk is as follows. I'm going to tell you what self-testing is, very briefly, which we've already kind of heard about. And then I'm going to tell you what we previously knew about self-testing and how the new results kind of fit in that framework. Then I'm going to briefly describe the method that we use. And then I'm going to tell you how to apply it to two specific examples, which we've already worked out. So this is the CHSH and the tripartite merman, and how these results improve on what we previously knew. And then at the end, there's going to be a short summary and future work slides. So what is self-testing? Well, so we start with the usual bipartite Bell scenario. So this is what we've seen already. And we are in this fully device-independent setting. So there are two parties. They receive inputs X and Y. They give outputs A and B. And as we heard before, somehow in the fully device-independent setting, this is entirely described by this conditional probability distribution. So this probability of AB given X, Y. And some people also refer to this as the behavior. And we call a behavior local if you can write it in this form where you basically have some hidden variable lambda and you sum over it, and then you have some kind of local response functions for Alice and Pippa. And conversely, if you cannot write it like this, we say that a distribution is non-local, or equivalently that it violates some Bell inequality. And so there's a very simple observation that if your state is separable, then whatever measurements you do on it, you always get local statistics. And that's basically because a separable decomposition of a quantum state gives you directly the local hidden variable model for it. Okay? So if my state is separable, then the statistics are local, and if you just take the contrapositive of that, you get that if your statistics are non-local, then your state must be entangled. Okay? And this is a very simple observation. And so now you might ask, okay, can I say anything more specific? Can I make any more refined statement? And essentially the answer to this question is self-testing. Okay? And just a short disclaimer. So actually I made these slides for another conference in a different country where you can actually use Google. I guess maybe in China you have to use something else. I don't know. Anyway, so from a mathematical point of view, self-testing is a very simple problem. You're given a conditional probability distribution, and you're promised that it comes from measuring some quantum state, and you're supposed to deduce some properties of the state or the measurement operators. And often, to make the problem simpler, just somehow to reduce the dimensionality of it, instead of giving you the entire probability distribution, somebody will just promise you a certain Bell violation, which is the linear combination of these probabilities. And so, you know, for example, and this is already known for for years. This was kind of observed by Popescu and Roy in '92. That if you look at the CHSH inequality, which is something that we've heard about in the previous talk, if you violate this inequality maximally, which is 2 square root of 2, then you can really say that the state that Alice and Bob share is equivalent to the maximally entangled state of the qubits. And of course, when I say that, you should ask, okay, so what is the exact meaning of this equivalence? And in order to understand this, you have to realize what are the inherent limitations of self-testing. And there's basically two. First limitation is that you cannot see auxiliary systems. Okay, so if your system has some degrees of freedom that your measurements basically ignore, then, well, you can never exclude them. And the other thing is that you cannot see local unitaries. Because if I apply some local unitary both to the state and the measurement operators, then obviously the probability distribution remains the same, but the state has changed. So in some sense, this is the minimum amount of freedom that you have to give to make some interesting self-testing statement. But what is cool is that this is actually sufficient. So basically, any state that violates the CHSH maximally can be written in this form. So this shows you the power of self-testing. So this is a very nice example. For the simplest Bell inequality, you get something very, very strong. And so, a more general question is, given this kind of condition on the probability distribution, what can you deduce about the state or the measurement? And let me just make a small remark that whenever you want to deduce something about a measurement, you have to do it kind of in relation to the state, okay? Because somehow you cannot deduce anything about the measurements outside of the support of the state. So somehow, any statement you make must also include this. And this is something that we heard about in the previous talk. For the purpose of this talk, we just care about the state. And then the general question is, okay, which states can be certified and how to do it? And for me, it's very important that your statements that you derive, that they are somehow robust, in the sense that maybe I can use them for an experiment, okay? So I want to have a robust state certification, and let me illustrate this with an example. So, for example, for the CHSH inequality, the classical value is 2, and the quantum value is 2 root 2. In 2009, there was a paper which showed that you can get a non-trivial statement about the state if beta exceeds 2.4. Okay, so this is, this is not too bad. This is basically halfway between the classical and the quantum. And then 3 years later, there was another paper which showed that you can say something non-trivial if your beta is epsilon close to the maximum, where this epsilon is of the order 10 to the minus 5. Okay, so it's pretty clear that from the experimental point of view, the first one is useful, while the second one isn't. And just to link to Susanna's talk, for example, in this recent Bell experiment that they did in Delft, they saw the value of 2.4 with some uncertainty. I mean, it's clear that the second result, like this, obviously doesn't apply to this result. But what I want to point out, it's not just that the value is too low. Like the statistical uncertainty is many orders of magnitude higher than the error tolerance of this result. Okay, and maybe this is a bit unfair because this experiment has very high statistical uncertainty. But as far as I know, most Bell experiments, whenever, the statistical uncertainty is usually much bigger than this number. So basically, I'm just trying to say these kind of results are very far from being useful for any kind of experimental, data. Okay, so previous results. So actually, there's quite a few states that we know how to self-test. So that includes the singlet, graph state, high-dimensional maximally entangled state, non-maximally entangled state of 2 qubits, and there's a couple more examples. But basically, all of them only apply if the statistics are perfect. So this is this epsilon of 10 to the minus 4. When you're looking for experimentally relevant results, there's actually much fewer of them. And basically, there's a single analytic result from 2009, and this is the one I mentioned, and I'm going to talk about this a bit more. And there's the swap trick. The swap trick is a numerical method based on the SDP hierarchies, which essentially allows you to derive a lower bound for any Bell inequality you like. So it's super versatile, but it's computationally expensive. So far people have tried it up to, I think, 4 qubits and 2 qubits, and it's clear that it doesn't scale very well. So you won't be able to deal with big systems using this method. And also it's computational, so it doesn't really give you much insight, about the results that you're getting. And by the way, if anyone's interested in these references, they are all in the paper, so please have a look. Okay, and so what we propose is a new approach for analytic self-testing bounds, which give improvement for the CHSH and for the tripartite Mermin. The tripartite Mermin result is actually tight in some sense, which I'll explain later, so that's pretty nice. And essentially, we reduce the self-testing problem to some operator inequalities. Okay, and before I get into the details, I want to define this measure, which I call extractability. This was proposed earlier, but people didn't really give it a name. I think extractability sounds cool because, first of all, it allows me to use the letter psi, which is not used very often, and also it makes it different from distillation. And this is like a one-step procedure. So basically, what Alice and Bob do, they apply some local extraction channels on their state. And then, on the input state, rho AB, and then they evaluate, okay, how close is this to the target state I want to get? So basically, I'm trying to extract target state psi from input state rho AB, and I'm allowed to use local operations. Okay, so this is a measure, and what's kind of good about this measure is, first of all, if it achieves the maximum value of 1, then this is equivalent to saying that my rho AB is of this form. So essentially, the target state is already in somewhere. It's just maybe kind of rotated away. So I just kind of find it. Okay, so this is pretty good because it coincides with what I showed you before. So that gives us hope that this is maybe the right definition. And also another nice property is that it has a simple kind of trivial lower bound. So basically, if my state rho AB is very bad, I can always just throw it away and replace it with some fixed state on Alice and fixed state on Bob. And then I can achieve at least the largest Schmidt coefficient squared. Okay, so it's a trivial lower bound, But it's a nice property because some other measures that people studied before don't have this property. So basically you cannot lower bound in the top. Okay, and so you have these local extraction channels, and it's a pretty natural idea to try to construct them from the measurement operators, because that's something, something that you're given. And essentially that's how the proof by Bardin from 2009 goes. So first of all, they prove some self-testing statement for 2 qubits, in which case basically they use the local observables to get a reference frame on their local qubits, and they derive some, they figure out what rotation I need to apply to make it align with my maximally entangled state. And then they use Jordan's lemma to show that the same bound actually holds in any finite dimension. And the bound they get is the following. Okay, so the gray lines, the gray dashed line, this is a trivial lower bound. This is an upper bound, which is kind of easy to show. And this is the result from 2009. Okay, so it's a straight line. It's certainly experimentally relevant because it goes down all the way to 2.4. And I think this is a very important result because it's really the first analytic self-testing bound which has kind of reasonable robustness. But for some reason it has been forgotten by the community. And this includes some of the authors. So that's why if you ever write a paper on self-testing, you should definitely include this. And basically what we're proposing is a refined version of that, okay? So we're going to say, yes, that local channels should be should they just depend on the measurement operators. And then if my target state is pure, I can play this trick where I write the fidelity as an inner product. And then instead of applying the actual channels to my input state, I can apply the dual channels to my target state. And this allows me to write this as a trace of 7 operator k, which looks like this, with my input state. And the good thing about k is that k doesn't depend on the input state. Okay, it depends on the target, it depends on the measurement operators, but it does not depend on the input state. And that's somehow good because one of the kind of notorious problems in self-testing is that you always have to consider both the measurements and the state together, and that's what makes the problem complicated. In this case, this is a convenient way of kind of splitting them up. And then you realize that the bell operator also doesn't depend on the state. I mean, this is kind of obvious, but so now you might think, okay, maybe I can somehow relate these 2 operators. And that's precisely what you're doing. So let's forget about the input state, and what I want to get is a statement like this. So I want to show an operator inequality for some parameters s and mu, some real numbers. So I want to show that k is greater than SW plus mu times identity. And I want it to hold for all possible measurement operators. I mean, obviously this is a challenging thing to prove, but if it works, then we're in good shape, because then you can basically trace this inequality with your state. And now, whatever the state is, it's going to work. That's kind of the power of this inequality. And basically, what you get on the left-hand side is some kind of fidelity, which is a lower bound on this extractability measure, whereas what you get on the right is the linear function of the bell violation. So this is precisely a linear self-testing state. So then it's clear that the main technical challenge of this method is to construct these local extraction channels and find these real parameters s and mu such that you can prove this for all possible measurement operators. And generally this is very hard and we don't really know how to do it, but if you can apply Jordan's lemma, which basically tells you that if we only have 2 binary observables per party, then you can somehow block diagonalize them together, and the blocks are of size at most 2, then we are, we've reached something which is tractable, because then each block, if you ignore the unitary rotations, which are not important from the self-testing point of view, then each block is just parameterized by an angle, so it's a from 0 to pi over 2. And this becomes tractable because now you have 1 parameter per party, so you can actually do it. And so, for example, for the CHSH, okay, how do we construct the channels? That's the first question. And of course you can, I could define them for you, but I'd rather give you some intuition of what they are trying to do. And basically what we found is that what works well is this kind of angle-dependent dephasing. Okay, so if my observables are either the same or they are kind of the same up to flipping one of the outcomes, then I'm going to kind of dephase fully in that basis. If they are maximally incompatible, so this is the setup that allows me to violate CHSH maximally, then I'm just going to leave them alone, so no dephasing at all. And if they are in the middle, so there's kind of partially incompatible, I'm going to do some partial dephasing. But now, depending, if they are kind of close, I'm going to use the axis in between them as the dephasing axis. Whereas if they are kind of closer to this setup, so they are, they are more like this, I'm going to use the perpendicular one to dephase it, okay? And the intuition is, I'm trying to dephase, but I'm not trying to introduce too much noise. So that's exactly why I align these axes like this. And basically, once I've assumed certain construction of channels, now I can find these real constants just numerically. I can just build these matrices, and I can check when they become, when this operator on equality becomes satisfied. And I found that the constants are these, and then you just have to prove it. And proving it is actually not so difficult, because this is a 2-parameter family of 4x4 matrices. Okay, so actually it's possible to, and they have some nice symmetries. So it's actually not too bad. And the last step is you plot the bound, and you realize that it's actually pretty good. So you can see that it significantly improves on the previous bounds, and also it kind of reaches quite closely to the upper bound. So there isn't so much space for improvement anymore. And in fact, when I started this project, when I started working on this, I was 100% sure that the upper bound, this gray line, is the correct answer. And I was very disappointed when I found that this method only using the red line. But then I kind of realized that, given what I learned about this problem when I was trying to construct these extraction maps, I realized that I can basically find counterexamples for the upper bound. So the gray line is kind of too good to be true. So at that point, I actually don't know what the real answer is. I don't think it's the red line. It's something in between, but it's also not the gray line. So I think I think it would be interesting to know the exact shape of this, but I suspect this is a very difficult problem. And maybe just one more thing. So before we knew that you can make a non-trivial statement about the state, if your beta exceeds, I think, 2.38, so this was this point, whereas now we pushed it down to 2.11. So there's still this region between 2 and 2.11 where we don't really know, but it's kind of much smaller. Okay, and then for the tripartite Merman case, it's actually very similar. So we use the same extraction channels, so this is kind of angle-dependent dephasing, and then, okay, you can find the S and V numerically, and then you have to prove this. And this is a bit more difficult because now it's a 3-parameter family of 8x8 matrices. But actually, you can show that these matrices, they have some nice block diagonalization, which is independent of the parameters. So somehow there's a generic, there's basically 4 2x2 blocks, and these blocks don't depend on these parameters. And so basically, you can examine each 2x2 subspace separately. And that's what makes it tractable, because on these subspaces you can just use these, these conditions for the trace and the determinant of your 2-dimensional matrix. And again, you plot it, and you realize that again it improves significantly on the previous bound. But what is even better is that this one is actually tight. Okay, so basically I can give you a family of states which interpolate between this point and this point, and they achieve the right Bell violation, and I can show that you cannot extract a better singlet, a better GHZ state, tripartite GHZ state than this. Okay, so in that sense, this is a tight relationship, and for me, this is just one extra piece of evidence that this is somehow a good measure for this problem. Okay, because if you find a nice linear relationship between the beta value and the and this extractability, this is somehow the right measure to use for this problem. And okay, I think this is summary. Maybe I'm going a bit too fast. But basically what we've done is, we've proposed a new method for obtaining analytic self-testing statements based on operator inequalities. And we have obtained improvements for the CHSH and the tripartite Merman case. And the Merman is actually tight. And this is like the first provably tight self-testing statement, which I think is pretty cool. What we're planning to do now, well, so this method definitely has more applications. So I think we could certainly certify n-partite GHZ states using the n-partite Merman inequality. And I've done some preliminary numerics. It seems to work. So I think basically you can apply all the same tricks, and then you end up with these matrices. So you just have to prove that certain operator inequalities hold. And this might be hard in general, but maybe for this very special case, this is possible. So I'm really hopeful about this. And I think also you could use the tilted CHSH inequality to certify non-maximally entangled 2-qubit states. So we know that for the perfect statistics, this is how it works, and I think now we could make it robust using this method. And note that this method, these two cases, because they are still fall in this scenarios of kind of Jordan's lemma, you know, 2 binary observables per party. So for these guys, somehow we already know how to do it. You just have to construct these matrices and then try to show that, you know, they are positive. And I think these can really work out. It's just a question of sitting down and working it out. The really big question is whether you can push this reasoning beyond Jordan's lemma. So basically, whether you can apply this to a scenario where there is maybe, you know, more measurements or measurements with more outcomes. And this is certainly hard. This is certainly hard, but I kind of believe, or I want to believe, that it's possible. And really, if you want to do it, you really have to understand how, you know, given some observables or some measurement operators on a high-dimensional space, how to construct some reasonable extraction channel from it. Okay, and at the moment, we really have no idea how to do it, but I believe this can be done. And you know, if anyone is interested, then please come and talk to me. And I think this is basically it. Thanks a lot again for having me here. Thanks for your attention, and I'm happy to take any questions.
Can you show the slide where you have the bound, the first one?
The CHSH? Yeah.
So you said you had a counterexample to the dotted gray line. Does that also mean that this green question mark is not going to go all the way down to 2 then?
Okay, so it's a good one. So it's a counterexample that works everywhere on this line except for the extreme points. Yeah, I mean, so actually we know that the extreme points are tight. We know that this is exactly 1. And we know that if you don't violate anything, then, you know, you could be not even entangled. But basically, for any non-trivial combination of these, I can give you a counterexample. It's a very simple thing, and it really, like, you know, the way I found it was really when I was trying to construct these example these extraction channels. It's just when you realize that you have more than a qubit, so basically this is like a counterexample for basically 2 qubits on each side. So it's really very simple. So it's basically, you know, 2 Jordan's blocks on each side. And what you're going to do is you're going to make one of these Jordan blocks like maximally incompatible, and the other one kind of fully compatible. And you realize that this combination allows you to achieve, you know, some kind of decent Bell violation, but it's actually very difficult to kind of maximally extract things from it. Just because, you know, if Alice knew which block Bob is in, and vice versa, that would be very easy, because if they could communicate the block labels, then they are back to the 2-qubit scenario. And for 2 qubits, actually even better bounds can hold. But the problem is, like, I only know my block, and you only know your block. But nevertheless, we have to do something which will work well for all kind of 4 combinations. And this is the trick. So yes, I have a counterexample, and this means that I really don't know what the true answer is. But I do believe that you get something non-trivial as soon as you violate it, as you exceed 2. But I don't know how to prove it. Somehow this is what quantum mechanics should be like, but I don't know how to prove it.
Thanks.
So I have a question.
Yeah.
So I think the extraction measure is very interesting, the way that you measure the outcome of the self-testing.
Yeah.
I'm curious how that relates to previous measures that have been used in self-testing results, like trace distance.
So, okay, so the problem is, yeah, so I guess you're talking about this trace distance from this Myers-Yao set.
Yeah, so like I've often seen self-testing results phrased in terms of trace distance to the ideal state tensored with the junk state.
Yeah, so the problem is I actually don't know. And actually this is something I want to investigate, but somehow I believe that those measures are just, yeah, okay, so what I like about this measure is that in order to evaluate it, you just need to, somehow in the end you have an unknown state of possibly big dimension, but you want to extract something of known dimension, like a singlet or a GZ state, okay? And this measure, to evaluate this measure, you just need to know the output of it, okay? So really, you put it through these channels, something comes out, and then you see, okay, how close is this to what I wanted to get? For all these other measures, in order to evaluate them, you do some unitary, and then there's the output and there's the junk, but somehow you need to, well, no, there's like, everything is mixed up. But basically you can think, okay, this register is mainly the output and this one might still contain junk. But in order to evaluate them, you still need to know the full state of your system. And I think that's actually the problem. So these are exactly the measures for which, it's very hard to get lower bounds, because we just, these optimization problems become very, very difficult. You have to go over like, you know, basically infinite dimensions. And so that's actually why I don't know the answer. I think it would be interesting to find out, but somehow I considered the previous measures just very, very inconvenient to work with. So that's why, I mean, I thought about this a bit, how these two are related, and there is a bound in one way. So, so this one is certainly like overestimate your closeness because you're essentially tracing out the jump register, but I don't know whether, you know, whether this can be a big difference in the other direction. But yeah, it's certainly something I want to look at.
Yeah, I can see how extraction may be easier to work with.
Yeah.
Other questions? Oh, one more.
So what's the intuition why you're using this kind of rephasing noise?
It's a very good question. I was waiting for it. And I was going to prepare a slide for it, but I didn't have time. So basically, yes, I also originally thought that what they should do, if you see, what is it? If you see something that's fully compatible, you know, so there's like no value violation, you should just kind of throw away the state. So do something like, you know, amplitude damping, just kind of map everything to the zero state. Okay? The problem is exactly this counterexample which I mentioned when I was answering Jonathan's question. So basically, if Alice and Bob have two subspaces each, one of them is maximally compatible, and then the other one is maximally incompatible. Okay, this kind of amplitude damping, where you basically erase your state and you replace it with a zero state. It works very well if if they both have the maximally compatible subspace. But it works very badly if one of them is trying to erase the state and the other one is trying to kind of preserve it so they don't touch it. Because then you end up with fidelity of basically 1/4. So you get something like 0, 0, tensor identity over 2. So that's why I started playing with other things, and this is what came out. So actually, yeah, I mean, why does it work? I don't know, but it works. But yeah, I mean, I was playing around with many different channels, and this seems to work well.
Question? What do you got, Mike?
I wonder if your method could be used to reproduce what people know about self-testing.
What do we know?
So the case result, for example, it's I think it's an asymptotic result for any epsilon. There's a self-testing statement.
Sorry, can you?
So even for SHM, I guess for more games, people have asymptotic results saying that if the score is epsilon close to optimal, then the state is epsilon prime close to optimal, right? And epsilon prime usually is square root of epsilon, right? So I wonder if your method could be used to reproduce that result, such results.
Well, I mean, so I guess I see it in a different way. I mean, so this method gives you much stronger results, but you have to work really hard, right? So I mean, I managed to work it out for 2 specific cases. So for the CHS and Mermin, and it gives you much stronger results than these other methods. I guess the methods that you're mentioning, they are kind of more generic. They are easier to use for a general setting, but you pay the price of the results being much weaker. So somehow I see it as kind of 2 alternative approaches. Either you go for a general method that gives you not so strong statements, or actually from my point of view, very weak statements, or you go for something that is specific for just some special cases, but then you can really get something which is experimentally relevant. And I think it's going to be difficult to find something that does both, I think.
So I want to understand what you mean, in what sense that your result is stronger. Is it when the error is really big, then the other result may not have implication, but you can deal with big error?
Yeah, that's what I'm saying. Yeah.
Okay, let's thank the speaker again.